Question number 11. Consider the following compounds A, B, C, D, E. They have given the relative molecular masses. E has a slightly higher relative mass. They have given some graphs. So the question is here: variation of boiling points of these compounds is best shown by. Right, now when we jump into the theory, the boiling point or the melting point depends on the strength of the interaction, the strength of the intermolecular interaction. Strength of the intermolecular interactions. Now the strength of the intermolecular interactions depend on 2 points. First one, the number of or the amount of intermolecular interactions. Amount. The second one, type of the intermolecular interaction. Now the amount means how many interactions are formed. The type means whether it's a hydrogen bond, ion dipole interaction, a dipole-dipole interaction, a London force, etc. Now the amount of the interaction depends on several points. First one, the number of electrons. Let's say first one, the number of atoms, the number of atoms. If a compound has more atoms, it can form more interactions. Therefore, the compound will have higher boiling points and melting points. The second one, the number of interactions. The number of electrons. If a species has more electrons, it can form more interactions. Therefore, the number of interactions will be higher, and therefore the boiling point will be higher, or the melting point. Next one, now you can put the molecular weight here. If the number of atoms is higher, the relative molecular mass is also higher, relative molecular mass. The third point is the surface area. The surface area. If the surface area of a species is greater, it can form more interactions, and therefore the boiling point will be higher, and also the melting point. Now the surface area can be found like this. If a molecule is linear or a long chain compound, higher surface area is there. Long chain has greater surface area. Greater surface area. Branched molecule will have a lesser surface area compared to the long chains. Right. The type of the interaction, the type of the intermolecular interactions depends on whether the molecule is polar or non-polar. Polar or non-polar, or whether it's ion. The ions have the highest interactions. The strength of the interaction will be highest in ions. Then polar molecules, then non-polar molecules. Now this is the theory behind finding the order of melting points or the boiling points of given compounds. So we have to compare these purple colored points in order to find the actual boiling point order of the given compounds. Now let's go to the compounds. We can see that A and B are hydrocarbons. They are just alkanes. C and D compounds are aldehydes. aldehydes, this is an alcohol. Now, as a general rule, if different types of organic compounds have slightly similar close enough relative molecular masses, the polarity governs the strength of the interaction or the boiling point or the melting point of the compound. Therefore, non-polar alkanes will have the lowest melting points. So A and B should have the lowest melting point. So from that point we can remove this answer, the fifth one, because they say D has the lowest boiling point. So D is actually an aldehyde, so the aldehyde cannot have the lowest boiling point with respect to alkanes, so A and B. Therefore this answer is out. And none of these are similar to each other, therefore they shouldn't have similar boiling points. Therefore this answer is out, because in this graph they say C and D have the same boiling point, and in the third graph they say A and B have the same boiling point. So these answers are also out. So the answer is either the second one or the fourth one. We can see that E has the highest boiling point. We can easily understand that because it has a higher relative molecular mass and it has an OH group. Its intermolecular interaction will be hydrogen bonds. None of the other compounds form hydrogen bonds with themselves. Therefore, E has the highest boiling point because its interaction is the strongest. Now C and D should have higher interactions, therefore higher boiling points than the alkanes. Now E has the highest one. Now let's compare the other two. Now A and B are both alkanes. They both form London forces. So from the type of the interaction we cannot find the correct answer. Let's go for the number of atoms. Both of them have the same number of atoms, same number of the same relative molecular mass, therefore the same number of electrons, and we have to go for the surface area point. Now A is a long chain alkane, B is a branched alkane. Now long chain alkanes have greater surface area. If I show you that the long chain alkanes have greater surface area because like this. Let's say this is a long chain hydrocarbon and they can be closely packed. Since they can be closely packed like this, they can form stronger London forces and also greater number of London forces like this. If we take a branched alkane like this, let's say this is a branched alkane. When you try to arrange them closer to each other, you can't arrange them very close to each other like we did in the linear chains because they are branched. So the number of London forces will be lesser and also the London force length is very long. If the length of an interaction is very high or very long, it becomes weaker. Now shorter London forces formed are stronger. Shorter London forces. These are longer London forces. London forces. And the number of London forces is lesser here. Therefore, branched compounds will have lesser number of interaction and as well as weaker interactions with respect to long chain hydrocarbons having interactions. So they are shorter and more stronger. Therefore, linear chain having compounds will have a higher boiling point. So A should have a higher boiling point than B. Therefore, this answer is also out. They say A has a smaller boiling point than B, but it cannot be true. Therefore, the answer should be the second one. Alright, let's go to the next question.